Hello and welcome to the Bourns presentation for Flyback topology highlights and Bourns solutions for low power conversion drivers. My name is Kyle Moldenhauer. I'm the product applications engineer for the Bourns technical marketing group, and I will be giving the presentation today. For a quick agenda, I'll be showing and describing basic flyback operation, followed by some of the magnetics design challenges for the transformer itself. After that, a matrix showing comparisons between push-pull and flyback topologies based on the transformer designs that I had just presented. And last, I will show Bourns product solutions and capabilities to produce flyback transformers and give a brief summary to close. So, basic circuit operation for flyback. It's a simplified schematic on the right side of the slide. And really, flyback operation is on the primary side of the transformer, which you can see the switch at when the switch turns on. The primary of the winding stores energy until which time the FET turns off, at which the primary of the circuit gives up its energy to the secondary side of the circuit, and the secondary side then discharges that energy to the output secondary side of the circuit. And so this flyback operation between the two really, to me, has a dual operation mode for the jobs that the flyback has to do. So really, you still have power conversion of a classic transformer to transfer energy in combination of voltage and current from input to output. But this flyback operation necessarily requires a transformer to supply energy while the switch is off. That's an energy storage aspect of it. So a flyback transformer often operates, or does operate, a lot like a single winding inductor or choke. And so then this brings up always the classic argument for a flyback transformer. Is it a classic transformer, or is it a more akin to two coupled inductors together that trade energy back and forth? Realistically, or the way that I conceptualize it, is it really does a bit of both, considering both modes of operation. And so that leads to these key factors for success. And one of the first things I think of when I'm designing transformers is to maintain signal integrity. Signal integrity in terms of parasitic effects and trade-offs that are needed for an effective coil design. So those affects and trade-offs really affect, EMC and EMI performance from the transformer itself. And then I'll be moving on to core gapping effects that are needed to complete the energy storage portion of the flyback transformer, and how that affects saturation current handling. And then finally go into isolation and safety requirements that need to be met within the confines of the transformer itself. And so this pulse wave anatomy is what I chose to show. So if you can imagine a well-behaved normal square wave coming in on the very left part of the slide, the red then would signify the output through the transformer. And so the leading edge then, responsibility in terms of parasitics, are mainly through the distributed capacitance and leakage inductance. Distributed capacitance being then the capacitance built up in the turns of a winding on either, let's say, the primary or the secondary in a two-winding device. Leakage inductance then determines the amount of coupling between those two windings, primary and secondary. So the more tightly coupled or more closely you put the windings together, the lower the leakage, and typically the better the transient response on that leading edge. Top of pulse then really is apportioned to load resistance at the output and then the magnetizing inductance. Usually you'll see a little bit of a droop or a dropping, so it's not a straight across at the top of pulse. So that's that parasitic affect. And then the backswing down, which is a negative overshoot, is a result of total winding resistance and then the discharge time of the magnetizing inductance and secondary distributed capacitance. A lot of importance is put on low leakage inductance for a flyback transformer design, In particular, that initial transient spike at the leading edge. So leakage inductances definitely affects that response at the beginning of the pulse. And so wanted to pay attention to that, but also that leakage inductance is frequency dependent. And so typical suppliers will give you leakage inductance in terms of the constant region, usually between 10 kilohertz and 100 kilohertz. But that doesn't necessarily help you either if your switching mode of operation may be 200 to 500 kilohertz for your supply, or you're looking to accurately depict EMI or conducted emissions through the transformer. You may be looking at a much higher frequency than that. So this slide is to really tell you that leakage inductance changes over frequency, especially in a high frequency region. So if you need information at a higher frequency, simply ask your supplier to run you a leakage inductance curve based on frequency. Then you can get the most accurate data to use in whatever application or applied information you need to know. So leakage inductance in conjunction with another new term called inner winding capacitance, which is another parasitic, which is the interaction or capacitance between the primary and secondary windings of the transformer. So what I've got here is a basic example to say we want lower leakage, better coupling with windings tightly together. However, that increases inner winding capacitance because the more closely we put the windings together, the higher the inner winding capacitance. Inner winding capacitance is a direct effect of increased conducting emissions from secondary to primary. So we want inner winding capacitance as low as possible. So I think you can start to see kind of the cyclic effect where, yes, we want both of these quantities as low as possible, but one tells us to put the windings closer together and the other one tells us to put them further apart. Now, in application to the actual circuit and how it is in there, you can see the L sub LK is the leakage inductance built up that we were talking about before that affects the leading edge transient response of the wave. But also there's other things like the capacitance between drain and source of the FET. You have distributed capacitance that can work in conjunction with the leakage inductance and the FET output capacitance for inclusion. The combination of which contributes to the self-resonant frequency of not only the circuit, but the distributed capacitance and leakage capacitance combined for the resonance frequency of the transformer. So while I agree, leakage needs to be kept as low as possible, other combinations of things can be used to, say, move the self-resonant frequency of the transformer out of the region of transient affect to reduce that. So what that might do is leave room for the inner winding capacitance to necessarily flex down a little bit, and that's depicted on the right-hand side of the slide here, which shows that the inner winding capacitance definitely affects conducted emissions and determines the size of the Y cap that needs to be used. So again, it's the balance between these two things that to me should really be evaluated, not simply to keep low leakage as low as possible, unless you want your Y cap as big as possible, or you need to put more noise reducing components in, like common mode chokes and differential mode chokes, because we sell those too, and we are happy to supply those from Bourns as well. So overall, this whole thing with Parasitic, it's trade-offs for everything else. And so while there is paid particular attention to one aspect of the parasitics, it really kind of needs to be an all-encompassing and global aspect that needs to be considered. So again, when you're working with your supplier on a given transformer design, they may only list leakage inductance for a flyback transformer, but ask for the rest of them. Distributed capacitance, inner winding capacitance for a complete evaluation of the transformer may be needed. So moving on to energy storage. This is another aspect of the transformer design itself, which affects the size of the core that can be used. So for energy storage then, we talk about affects of being able to increase the saturation current handling of a given core. So what that means is introduce an effective air gap in the core. So you're lowering the reluctance of the core, thereby increasing the amount of current handling by methodology of what I have up here as a BH loop for operation. So the yellow line really would kind of be an original ungapped state of the core, as opposed to the green line, which we call the shearing of the BH loop, really to increase the amount of saturation current handling, which is the horizontal axis, or its field strength. And so by doing that, then you definitely increase the amount of current that can be handled through a given core size, but at the detriment of losing permeability at the same time. And so this slide depicts that while the field strength on the bottom, so green to purple, increases the amount of current handling for a given core, the green to purple line also signifies a decrease of permeability, which decreases the amount of inductance per turn of wire that you put on. So to maintain a given inductance per current, you need to add more turns on the core itself as you increase the gap length in the core halves. Then there's even another parasitic effect of gapping, which is fringing flux. And so what this is the energy transfer across the gap. Not all of the energy is fully translated through magnetic flux from one side of the gap to the other. So you have this leakage effect that way. So the detriment there is a center for noise or harmonic distortion. So what the thinking is, or what you will really want to do in reality, is the gray circles represent the windings in this picture. And so what you want to do is move the windings out of the way of the fringing flux. And so that's fine, except that what it's going to do is create space within the bobbin itself. So there's different techniques you can do to try to take this fringing effect out of the center core to affect the windings by using different layers of tape and different techniques. But it's also something that needs to be considered in the transformer design in relation to the rest of these parasitics that we've already talked about. So yes, we're getting kind of complex for things that needs to be thought about for one little transformer. So the last thing we're going to consider then is isolation and safety. So I've chosen a battery management system here as the example. Bottom of the slide is the low voltage battery side. The top is the high voltage battery pack side. In between those two, safety dictates a level of galvanic isolation or protection of the user from electric shock. So you need to decide, how am I going to do this in my circuit? Typically, the transformer is chosen to do that job within the circuit itself. So we're more than happy to help you do that, but we need to ask you some questions in order to select the right transformer. So one of the first of which is to establish what your peak working voltage is, or really the highest input voltage to the primary, or that the primary of the transformer will see. If it's enough, either through a transient state of an open or closed circuit operation, it may have to contribute to an over voltage category, which is part of the standard itself. And then that would be akin to more stringent testing, or maybe an increase of creepage and clearance distance, which I can move into in the bottom left part of the slide. So distance per a safety standard is in terms of creepage and clearance. So clearance is defined as distance between two objects or two parts of the transformer through air alone. Creepage then is that distance between two different surfaces, or two different points along a surface, so not just through air. So it takes into account a different criteria per the table in the standard. So those combinations of things, and then also given the level of insulation, which, from a customer aspect, we'll ask, does it need to meet a functional level of insulation? Does the transformer only need to operate in circuit? Which means it would be dedicated to a lesser amount of creepage and clearance distance, as opposed to a reinforced isolation requirement, which has 3 layers of user protection from electric shock. Well, that obviously is going to need an increase of physical distance per the table in the standard. Then any extra operating conditions you might have, regardless of other criteria that you have for safety, is does it have to operate so many meters above sea level? What's the pollution degree or the dirtiness of the environment that the transformer is going to operate in? And then any other specific tests that you may need. Partial discharge or reliability or environmental testing that needs to happen as well. So methods to meet distance now, back to safety. With these physical distance criteria, it manifests itself really in the makeup of the bobbin specifically to the transformer in relation to the core and the windings. And so this is where you'll have different looks of a transformer. The top left is an example of meeting creepage and clearance distances equally between the primary and secondary side of the transformer, as opposed to the bottom left, which has decided to put safety incorporated only to one side, either primary or secondary. So this is where extended rails of bobbins come on and kind of the different look of a transformer may be used. Secondary then is annex exceptions then, which we start to have the conversations of triple insulated and fully insulated wire to wind with, which means that the wire itself has separate extruded layers on top to meet insulation requirements in lieu of physical distance. And so let's say you have 8 millimeters of creepage and clearance, the wire winding on a given primary or secondary, that distance would go to 0 using this type of wire. Same thing with tape. Layers of tape would meet the same annex exceptions in lieu of distance. Then lastly, any type of a seal joint or encapsulation, it can be used to replace distance as well. That's through the use of encapsulants or conformal coatings, over moldings and transfer moldings. And then finally, to say that safety doesn't necessarily have to be incorporated in the transformer. So the PCB can be used to create that as well with other air gaps and dams, in addition to incorporation of safety into the transformer itself. Then quickly to move to this topology comparison, and just a really quick matrix of it's not a set thing that I tried to come up with to say where am I going to use this, or how am I going to decide what topology I want to use for my design. And really this just gives different criteria for power level and emissions and regulation to really serve as a hopeful light guide in your quest to find the right topology that you want to use for your application. So moving on to flyback solutions from Bourns. In any DC-DC flyback, especially for these low power applications, there is a plethora of IC choices that you can use with different chipsets from all the IC manufacturers out there. We really have flyback transform approvals at most of them, many of which we have reference designs already approved to choose from. In our catalog product range, I wanted to highlight our configurable transformer, which is really 6 equal windings in one transformer body that you can use to hook up in different wired configurations for turns ratios, inductance levels, and current handling. So it gives you an option to kind of experiment with a transformer design before maybe making that decision to move to a custom design, or maybe this will work out right for you. Then we have specific catalog flyback solutions meant to be used with specific chipsets or applications. The one on the right is a PoE example for our flyback. Does it have to be used for only PoE? Not necessarily. If the criteria and the size meet your condition for say an IoT application, feel free to use that as well. Again, this is just a guideline for our catalog for the different uses that it was originally designed. Then to highlight our custom flyback transformers, we've got all different sorts of industry standard core packages that we can use for transformer design, and then the ability to do any type of tooling that you would need either for core and bobbin to meet your requirements. At this point, you're probably looking at a custom transformer design, but we can incorporate levels of custom, we call it, whether using a standard core on a tooled bobbin, or maybe a regular bobbin on a different type of core look that you've seen before than what it was designed for. So kind of different combinations there really incorporate our custom transformer design services that we can utilize in manufacturing, on our automated assembly lines or manual processes to a high degree of quality, for winding and testing. And then advanced measurement capabilities that we have to offer you in order to fulfill your needs and really get you the most information that you're looking for as a service from Bourns. So to summarize, magnetics involves multiple design trade-offs for the parasitics we talked about before. Those trade-offs affect the overall size and performance of the component. And the effects of core gapping really need to be considered for flyback operations specifically. And then safety and isolation play a large part of that design process as well. So a lot of things taken into account for a given application that you would need a transformer for. Automotive requirements can be a special case, like for BMS, for example. And then separation requirements between low voltage and high voltage can be implemented, several ways. It's just typically the transformer's job to be sought on to do that. And to finalize, Bourns offers a multitude of flyback transformer solutions, either through our catalog and distribution options or directly through our expertise in custom transformer design. So thank you for taking the time to listen to this presentation. And if you have any questions, please contact Bourns and we can direct you to the proper person to help.